Two forces of 4 newtons and 8 newtons act on an object. They can be replaced by a single force, which has the same effect as the other two forces. The resultant must have a magnitude of. Remember, we're going to add the two together, so we're going to get 12. And if we are subtracting them, we'll get 4. So it'll be anything between 4 and 12. A body moving at a constant velocity on a horizontal plane has a number of unequal forces acting on it. Which of the following statements is true? If it's going at a constant velocity, that means that all the forces are in equilibrium. So there is a zero resultant force. So let's read that through. The resultant of the forces is 0. That sounds pretty good. Friction between the body and the plane causes the resultant force. No. At least two of the forces must be acting in the same direction. I'm not sure why. The vector sum of the forces causes a resultant force, which acts in the direction of motion. No, there's no resultant force. So the only correct answer is B. Choose the system of forces that gives the mass m the greatest acceleration. So we're just going to land up doing subtractions over here and additions. So here we add them because they're in the same direction. Over here we're going to subtract, and we're going to, because they're in opposite directions. Here we are adding because they are in the same direction. And here we are going to subtract because they are in opposite directions. So the greatest acceleration will come from the greatest force. So the correct answer is, we've got a sphere. It's attached to a string which is suspended by a horizontal ceiling as shown in the diagram. The reaction force to the gravitational force exerted by the Earth on the sphere. So the Earth exerts a force on the sphere exerts an equal but opposite force onto the Earth. So it is the force of the sphere on the Earth that is the counteracting force of that. And we've got Kim as a passenger on an aeroplane, which is accelerating along the runway during takeoff. Which free body diagram correctly shows the forces that act on Kim if the plane accelerates along the runway? Well, Kim is going to land up. By the way, inertia is not a force. So as a result, we can cancel both of these over here. And the force of Kim on the seat is worthwhile, but it's not a force that actually is going to cause her to move in any way along. It's a force of Kim onto the seat. It isn't a force of the seat onto Kim. Remember, these are the forces that act on Kim. So the only forces that act on Kim is the Earth attracting her, a normal force pushing her back up, and the back of the seat on Kim, which drives her forward. So A is your correct answer. We have this dynamics trolley, and we use a ticker timer that vibrates at 20 Hertz, so we can immediately work out the period. 1 over 20 is equal to 0.05 seconds. It's left a series of dots on a length of tape pulled through the timer mechanism. Parallel lines are drawn through the dots, and the position of these lines was determined using a meter rule. So we've got the dots, there they go, all the way along, and as you can see, they're spreading out over here, and this is the ruler that it is working along. Write down the position of each of the dots marked A, B, C, etc. So A is at 1,4, and it's centimeters. So I'm just going to write 1,4, 2,0, 2,8, 3,8, and 5,0. When I work out AB, I then can say 2 minus 1,4, 0,6, 0,8, 1,0, 1,2. From what information can you see that the acceleration of the tape was uniform, that there are equal changes in the length of each interval? So you add 0.2, you add 0.2, you add 0.2. Calculate the magnitude of the instantaneous velocity of the tape when the dot marked C was made. So where is C? C is exactly in between B and D. So we are going to work out the velocity from B to D, and that turns out to be 0,018 meters. In other words, I go and I add B to C and C to D, and I divide that by the time period, and from B to D there are 2 spaces of 0,02, and I land up with 0,18 meters per second. Then calculate the acceleration of the tape. I'm going to need another piece of information, and I decided to work out first the velocity at a.5 and then work it out at d.5. So I went for a.5 and I went for d.5 and worked out the acceleration at both points, at least the velocity at both points. So it becomes 0,006 divided by 0,05. It is one space, and it turns out to be 0,12 meters per second. That is the average from A to B, which it means it is true at a.5. So that was my 0,6. Now I'm going to work out from D to E, and I go 0,012, because I have to get it into meters, divided by the time, 0,05, and I land up with 0,24 meters per second. And where is that true? At d.5. And finally, I say acceleration is final velocity minus initial velocity divided by the time. Well, from a.5 to d.5 is to b.5, c.5, d.5. It's 3 spaces, 0,05, and I land up with an acceleration of 0,8 meters per second squared. We've got 2 blocks over here. They are identical, and they're not 6 kilograms. Each one's 6 kilograms, and the other one is 4 kilograms. Sorry, that's my mistake. They are dragged along the rough surface by a 60 Newton force acting at 60 degrees to the horizontal. Well, the first thing I need to do is work out the component over here, and I use cos of 60 times 60, and I get 30 newtons. The next thing that I'm going to do is I'm told that I've got 16 newtons acting in this string in that direction, and obviously it's acting in that direction as well. Then I need to say force resultant is equal to 4 times A for block A, which is also equal to the big force, 16 newtons, which is pulling it forwards, minus the small force, which is the frictional force. They tell me this object is accelerating at 2 meters per second squared. When I rearrange that, I get 8 newtons. Simultaneously, the force resultant of block B is 6 times the acceleration 2, which is equal to 30 minus 16 minus friction, because remember, friction is going to act there, and it's going to act over there. So I land up then, when I resolve my frictional force, to find that it is 2 newtons. There's less friction. Why? Because I'm partly lifting that off the ground. I've got 2 masses over here. Sorry, your 6 kilograms and 10 kilograms had been left out. Draw a free body diagram to show all the forces acting on the 6 kilogram mass. Free body, I draw a dot. There is a weight, and there is a tension, and there is a further tension acting downwards. So it's T2 and T1 that are pulling on the 6 kilogram force. What is the tension T1 between the winch and the 6 kilogram mass when the winch is stationary? So I can say T1 is equal to, if you think about it, you don't have to break that up into its parts. It's really a 16 kilogram mass piece hanging off T1 over there. So it's 16 9,8 meters per second squared, because it's just a weight acting down, and I land up with 156,8 newtons up. What is the tension T2 between the two blocks? Well, now I need to break up each block. So first, let's look at the 10 kilogram block. For the 10 kilogram block, I'm going to say force resultant is equal to the big force, which is the weight, divided by the small force, which is the tension. Weight minus the tension, because this whole thing is being winched down, so it's going downwards. And then we land up saying that we have got 98 newtons minus a tension that I don't know. But the force resultant is this whole thing is standing still actually at this point. The winch is initially stationary. It may go downwards later. So I've done it that way around, and we land up with no resultant force, and therefore the tension is equal to 98 newtons. Now, if I'm taking a look at the 6 kilogram block, it only wanted T2. We've already got T1, so we're done. The winch now starts to wind the masses up. They are accelerated upwards at 2 meters per second squared. What is the tension now? Now I can say force resultant is equal to the tension, which it's going up is big, minus the weight going down, which is small, and I land up with 16 kilograms multiplied by 2 is the tension minus 16 times 9,8. And therefore my tension is going to be 188,8 newtons.